In this example, we'll look at how FlowEFD, Siemens CAD-embedded CFD tool for solid edge, can be used to analyze a flow and thermal management problem of a sewing machine from Bernina. FlowEFD combines all simulation steps, starting from directly using your solid edge CAD data for model preparation to mesh generation, solving, and results visualization, all in one easy-to-use workflow within Solid Edge. Let's take a look at our Solid Edge model. You'll notice that because of the FlowEFD add-in, there are a few additions to the interface, like the Flow Analysis tab for the command ribbon and the FlowEFD tab for the edge bar. What you will see as we set up the CFD problem and ultimately look at the results is that FlowEFD ends up feeling like an extension of your already familiar Solid Edge environment. And one of the keys to that is being able to work directly with your native Solid Edge model. A convenient way to create a FlowEFD project is to use the wizard, which guides you through the setup of the basic definition of your analysis. First, you will name the project, then select a unit system. Next, you will define the analysis type. The airspace around the sewing machine as well as within it will be considered in the problem. Since the sewing machine chassis has many openings, the internal airspace is connected to the external airspace. So this problem can be defined as an external analysis. Also, we will include conduction effects, so we will select heat conduction in solids. And since a fan is used for cooling, we will also include rotation. Next, we'll choose the fluid in the analysis to be air and select the default solid material. We can accept the default conditions for the walls and initial conditions and finish the wizard. This will create our project in the FlowEFD tree named Case 1. Now we need to finish setting up the model by assigning the remaining inputs. We can start with the Computational Domain, which was sized automatically around the model for an external flow problem. We can conveniently adjust the domain to be a bit closer to the model by dragging the handles of the domain boundaries. The next item to address as we work our way down the input data tree is assigning a rotating region to model the fan. We have created an axisymmetric object in Solid Edge that surrounds the fan blades and identifies the rotating region of the model. We can right-click and choose Insert Rotating Region. Here, we will select the component for the rotating region and assign it an RPM. Material properties can be assigned to the solids in a similar manner. So, for example, let's assign a material to the motor. I'll pre-select the components from the Pathfinder, then right-click on Solid Materials and choose Insert Solid Material. From here, we can browse into the engineering database and choose the appropriate material. The same procedure can be used to assign materials to the remaining relevant parts. Next, we can assign our heat source. The main item of interest that is generating heat is the motor. So we can go ahead and right-click on Heat Sources and choose Insert Volume Source. From here, we can choose the solid component that fills the interior of the motor and assign it a heat generation rate. The last main inputs to assign would be some goals, which serve a couple of purposes. One, they are a way of extracting from the analysis quantities of interest. For example, we want to know how hot the motor will get, so we can assign a volume goal of average temperature of solid for that component. The other purpose of goals is to help guide the convergence of the run, meaning that the solver will look for these goals to reach a steady solution before determining that the solver phase of the analysis is complete. At this point, we can run the analysis. This phase will include the meshing of the model and then the computations which lead to reaching a converged solution for the flow and thermal field. After the run, we can go ahead and look at the results. Let's start by looking at a cut plot, which plots the results on a selected plane. So this is showing us the velocity field, with the colors indicating the speed of the flow, with red being higher speed flow, as expected near the fan. Additionally, vectors show you direction of the airflow. We can dynamically slide the plane through the model to see results at other locations of interest. Now, let's change our plotting parameter to be temperature, while leaving the velocity vectors visible as well. And I'll add some surface plots so that we can see the solid temperatures for selected interior components of the model. Of course, we can see that the motor is the hottest component as expected. We can rotate the model around to look at the temperature distribution from different angles, as well as change our solid edge viewing option to be wireframe. If we want to show the temperature at a specific location, we can use the probe tool, which lets you float the pointer over any part of the model and get a dynamic reporting of the parameter being plotted. Now, let's change to another type of post-processing called flow trajectories, which gives a good three-dimensional visualization of the flow field and lets the designer begin to evaluate the ventilation effectiveness of his design. For more control of the animation, you can open the Animation tool. From here, you can choose the scenario and plots you would like to animate and save them to an AVI file. Flow EFD brings the power of CFD to solid edge users and allows engineers to make earlier, better decisions about the effectiveness of their design. Start front-loading CFD into your design process with Flow EFD.